In this video, we're going to be discussing measures of spread. So the first measure of spread that we're going to talk about is a very simple measure called the range. And the range is really pretty basic. It's just a subtraction problem. It shows how spread out the data is between the highest and the lowest value. So to find range, we subtract the highest number minus the lowest number. So that's all we do to find the range, is just subtract the biggest number in the data set minus the smallest number in the data set. So here's an example, and you can see the answers too. They're just basic subtraction. But it says in the table below, the average monthly temperatures are listed for each month for San Francisco and St. Louis, or St. Louis. So you can see the average temperature for January in San Francisco was 51, but in St. Louis it was only 30 degrees. In February it was 54 in San Francisco, but 35 in St. Louis. So you can see the average temperature for each month for both of these cities. So it says find the range of San Francisco and find the range for St. Louis. So for San Francisco, the highest temperature was only 63 and the lowest temperature was 51. So we just do highest number, 63, minus lowest number, 51, and we got a range of 12. So basically, what this tells us is that the data is not very spread out. The temperatures seem to be consistently close to the same values every day or every month. They don't vary very much. So you can probably have one seasoned wardrobe in your closet. You don't need to break out big jackets or anything, or breaking out summer clothes either. Pretty much you can dress like it's spring or fall all year long, I'm guessing, because the data just ranges between 51 and 63 all year. Now, St. Louis is different. The highest number in St. Louis is 79, and the lowest number is 30, so when we subtract that, we get 49. So this does have a bigger range, which means that if you live there, you would have different season clothes. Now, range is fairly easy to find, but because it only uses 2 data values in the data set, and usually there's so many more, we don't use it very often in practice. So what kind of spread do we use? We like to use standard deviation. So this is what standard deviation is. Standard deviation is the average distance of the data points from the mean, from the center. So basically, it's like finding the average distance each of the data values is from the mean. Finding the distance each data value is from the mean, and then finding the average of those distances. And so there is a formula for this, but we actually are going to use Rguroo to calculate the standard deviation. I'll tell you there are 2 types of standard deviation. There's the sample standard deviation, and then there is the population standard deviation. All right, and so the notations for these, the sample standard deviation is S, and the population standard deviation is this symbol here. It looks like an O with a loop at the top or something like that. This is lowercase sigma. I told you there'd be a lowercase sigma in an earlier video, and it stands for population standard deviation. Now it's the formula. It's not necessarily hard to do, but it is very tedious because you have to find the difference of each individual data value, and that takes time. There's some other things that are involved in the formula that make it a lengthy formula to use. So we're definitely going to use technology for that. I will tell you that the sample standard deviation formula and the population standard deviation formula are both slightly different, so you get different answers for each. So you definitely need to pay attention to which type of standard deviation you're looking for so that you give the correct one, since there are two and they will be different answers. So for standard deviation, basically you find it the same way that we found the mean, median, and mode. It's both the standard deviation for the population and for the sample. They're both listed in the choices for the numerical summary. So this is just kind of a review of how we did mean, median, and mode, but you're going to see that you will do standard deviation the same way. So first you make sure your data is entered, and then you go to analytics and you choose numerical summaries, and then you choose the variable that you are interested in finding the standard deviations for. In this case, we chose calories, and we moved it from the center column over to the selected column. Once we do that, we click the univariate button, and then this will pop up, and then you'll click any statistics you're interested in. You can see here I click population standard deviation and sample standard deviation, and once you do, you have those numbers here. Okay, so I want to illustrate that with Rguroo. So we'll go to Analytics, choose Analysis, Numerical Summaries. You need to choose a data set. I'm going to choose the serial data set that we've used in videos in the past. You can name your data summary if you want. I'm just going to leave it as is. I'm going to move calories over to the far right, and then I'm going to click univariate, and then I'm going to choose population standard deviation and sample standard deviation. Both are in the center column here, and then view, and there we have it. That's all there is to it. But you'll notice that population standard deviation 40.20849 is slightly different than the sample standard deviation, which is 40.4891. Okay, so let's look at this example. Below are a list of battery lifetimes and hours for a population of 6 batteries. So we know we're doing a population standard deviation. Battery lifetimes are 3, 4, 6, 5, 4, and 2. So we're going to do this in Rguroo. So first we need to start by entering the data in the data set. Okay, so you can see I've added the data set and I've labeled it as battery lifetimes. You can see it's now here at the bottom of my data. All right, I'm going to close it out. So I'm going to go to Analytics, click on the drop down, choose Numerical Summaries. I'm going to choose my new data set, which is really way far down at the bottom, battery lifetimes. And then we're going to move the variable, which I named hours of battery life, over to the far right. And then I'll click on univariate, and then I want the population standard deviation. And there we have it, 1.291 if we were to round. Okay, so there we go. So here's one. The ages of 10 fifth grade students are given below, and you can see all of the numbers here. You're going to do the same exact thing that we just did to find this. It ends up being 0.699, but in order to do this, you need to choose sample standard deviation instead of population standard deviation, and that will give you this answer here. So recall in a previous video when we talked about measures of center, we talked about statistics that were resistant to outliers. Median was resistant, but mean wasn't. Speaking of standard deviation, it is not resistant. That means that it will be affected by outliers. So outliers do have an effect on the standard deviation, and that's important to note. All right, moving on to the next thing is z-scores. Z-scores is really a measure of position, but the formula for z-scores uses standard deviation, which is a measures of spread. So that's why I've put that in this particular section. So for an introduction, think of this following scenario. Who scored better on their test? A student who made an 1100 on their SAT or a student who made a 22 on their ACT? So if you're not aware, there are two college readiness exams. One is an SAT, which some of you may have taken. The other is an ACT, which others of you may have taken. Some of you may not have taken it at all, but they are the two big tests. And while they test on similar things, the way they score, their scoring system is completely different. So for the SAT, you can score in over 1,000. The SAT, I think the highest you can score is 36. So if you're trying to compare two scores, an SAT score to an ACT score is not necessarily an easy thing because, again, they're scored completely different on different scales and everything. So this is where z-scores come in. They can be a way for us to make comparisons of things like this that are calculated on different types of scales. So z-score, what is it? So a z-score of a data value is the number of standard deviations away from the mean that a data value is. There is a formula here, but let me just kind of draw a number line here. And if here's the mean in the middle. I don't know what that is. We'll just say, let's pretend the mean is 20. Just put that up here. The mean is 20. And then we'll say the standard deviation is 3. So if I go up one standard deviation, which is 3, so that will take me to 23, right? At 23, that's a z-score of 1. And so what that means is 23 is 1 standard deviation above the mean. If I go up 3 more to 26, that's gone up 2 standard deviations. So that's a z-score of 2. That's what z-scores are. And you can have positive z-scores that go above the mean, and you can have negative z-scores. So if I go 3 lower than 20, I get 17. I've gone down 1 standard deviation. That's 1 standard deviation below. That will be a z-score of -1. So you can have z-scores that are positive, z-scores are negative, and basically z-score is just a distance. It's a distance a data value in the data set is from its mean, but it's measured in the number of standard deviations. Okay, so there is a formula to find this. Okay, you don't necessarily have to draw a number line out like that and try to figure it out. You can use this nice formula here for a z-score. And then hopefully you'll recognize some of these symbols and notations. So we have z-score equals x. So if you will recall, x represents an individual data value. So this would be the data value that you're trying to convert to a z-score, such as this 23 right here. If you were trying to convert that to a z-score, and we already said that's a z-score of 1, but if you didn't know that, you would put that in this formula for x to start the calculation. The next notation is mu. If you will recall, that's the population mean. I'm writing POP for short. And then that's followed by dividing by sigma, lowercase sigma, which is your population standard deviation. So again, some shorthand there. But that's what each of those values mean, and that's how you would find the z-score. So I just want to show you real quick, up top here, I had illustrated a number line with the mean of 20 in the middle, standard deviation of 3. So if we went up 3, that's 1 standard deviation, z-score of 1. If we went up 3 more to 26, that's a z-score of 2. I just want to show you how 23 is a z-score of 1 using this formula. So with the formula, we have, I'm just going to go over to the left-hand side here. We have the z-score, I'll write z for short, is equal to x minus mu over sigma. So the z-score for 23. So what you can do is you can just kind of write 23 as a subscript so you know that's what you're finding the z-score for. Because some problems you'll find multiple z-scores in one thing. So it's helpful to identify which one you're finding. So we would do x, which is 23, minus the mean. The mean, if you'll recall, is 20, divided by the standard deviation, which is 3. And so then we'll just going to come down here and do your 23 minus 20 would be 3. And then 3 over 3 is a z-score of 1, exactly what I said it was here. That will also work for a z-score of 2 being is the z-score for 26. So 2 is the z-score for 26. If you replaced in this formula, if I had this 26 minus 20, I would get 6, and 6 over 3 would be this 2 here. So the formula definitely works, and it's just a quick subtraction followed by division. So make sure you do the subtraction first, figure out that total, then do the division. Note that z-scores can be negative or positive. Like I said, if it's above the mean, it's positive. If it's below the mean, it's negative. So a z-score of -2 is 2 standard deviations below the mean, and a z-score of 1 is 1 standard deviation above the mean. So negative z-scores would be data values that are below the mean, and then positive z-scores would be data values above the mean. So let's look at how we can use these z-scores. Let's look at this problem, SAT or ACT. The national mean SAT score is 1083 with a standard deviation of 194. The national mean ACT score is 20.8 with a standard deviation of 4.8. Who did better relative to the type of test they took? A student who made an 1100 on their SAT or a student who made a 22 on their ACT? So we're trying to figure out who did better, this person who made 1100 on the SAT or this person who made a 22 on their ACT. So which one's better? And like we said before, earlier, the SAT and the ACT are scored completely different. So it's really hard to do this comparison. But z-scores can help. So the first thing that we're going to do is we're going to find the z-score for the SAT student, and we're going to find the z-score for the ACT student, remembering that the z-score formula is x minus the mean over the standard deviation, which is sigma. So we know the score of the SAT we want to change is 1100. The score of the ACT we want to change to a z-score is 22. And we know that the mean of the SAT score, so things that are important, the SAT mean is 1083. The ACT mean is 20.8. The standard deviation for the SAT is 194, and the standard deviation for the ACT is 4.8. Hopefully I said all of that right. ACT, SAT, getting a little confusing there. All right, so for the first one, we're going to start off with our X for the SAT z-score. So our X for the SAT is the data value we're interested in changing, which is 1100. And we're going to subtract the mean. The mean of the SAT is 1083. So we're going to subtract 1083 divided by the standard deviation, which is 194. All right, so if we subtract 1100 minus 1083, we get 17 divided by 194. And when you divide that out, the z-score for the SAT is a decimal answer. It is 0.0876. Usually for z-scores, we round to at least 2. This one is rounded out to 4. You want to pay attention to whatever work you're doing. If they have a preference for the answer, they will usually give that into the direction and tell you how they want you to round. Let's go to the ACT. The ACT score we're changing is 22. So that's our X minus the SAT mean. The SAT, I'm sorry, I'm saying SAT and I should be saying ACT. See, I told you I was getting confused there. So the Z-score for the ACT, we're changing the ACT score of 22 to a Z-score. So 22 is our X minus the mean of the ACT is 20.8. And we're then dividing that by the standard deviation for the ACT, which is 4.8. So if we do our subtraction on top first, make sure you do the full subtraction. We're going to do 22 minus 20.8, and we're going to get 1.2 divided by 4.8. And when you do that, the z-score for the ACT becomes 0.25. All right, so you might be thinking, how does that help? So what you can do is, now that they are converted to the same type of score. So we had SAT scores were on a certain type of scale. ACT scores were on another type of scale. We've now put them both on the Z-score scale. So if we draw a number line, now if I were to convert the mean of either of these to a Z-score, like let's say this 1083, if I converted that to a Z-score, 1083 minus the mean, which is also 1083, is 0, and 0 divided by anything is 0. So the z-scores for both of those is 0. So this represents, right here in the middle, this represents the mean. All right. So here's a 1, and here's I'm going to say 1 is here. There's a half. So if we were graphing the 0.08, I would say 0.08 is really close to 0 right here. So I'm going to put, that's the SAT. I'm going to put S for SAT. And then 0.25 is halfway between 0 and the halfway mark. So the halfway mark is here, right? So halfway between that is about there. So there's the ACT score. So which one is more higher than the mean? So 0.25 is larger than the 0.0876. It's farther above the mean than the SAT score is. So that means that the person who scored 22 on the ACT is better than the SAT score of 1100. So relative to each of their tests, the ACT, we would say that score of 22 is better than a score of 1100 on the SAT based off of these means and standard deviations. All right, so let's look at another one. We've got a baseball team and their ages. The ages of each of the players are below. So it says find the mean and the standard deviation, and then find the value that is one standard deviation below the mean. So why don't you go ahead and pause this? You can use Rguroo to find the mean. And what kind of standard deviation will we find? Well, this is the ages of all the players, of each player from the baseball team. So this would be a population. So you want to find the mean and the population standard deviation. So go ahead and pause the video, and when you come back, we will check your answers. Okay, so I've got Rguroo open. I'm just really quick review how to find the mean and the standard deviation fairly quickly with you. First, I went to data. I chose data import, create a new data set, and then you can see that I added baseball team ages here. So that's in my data set, or one of my data sets. So now when I want to find the mean and the standard deviation, I go to analytics. In the analysis dropdown, I choose numerical summaries. I'm going to choose my data set, baseball team ages, again, that I added. I'm going to move the variable, which is ages, over to the selected column and choose univariate. And then I want the mean. And then again, there's sample standard deviation, and there's population standard deviation. I want population standard deviation because this is the population of all the ages of every person in the baseball team, or on the baseball team. Hit preview, and it looks like we get 30.68 and 5.971398. If you'll recall, when you round mean, you go one place past the numbers in the data set. So the number, how they're rounded, the numbers in the data set were whole numbers, so I need to go one. So this would actually be 30.7 with a population standard deviation of 5.97. Okay, so here we have those numbers. The mean is 30.7, standard deviation is 5.97. So it just is find the value that is one standard deviation below the mean. So that would be a z-score of -1, one standard deviation below the mean. So really all we need to do here is just one below the mean, one standard deviation below the mean, is just subtract one standard deviation from the mean. So subtract 30.7 minus 5.97, and we get 24.73. Alright, so this would have a z-score of -1. Z-score of -1 because it's one below the mean. Okay, so z-scores continued. In the baseball team age problem set from example 2, so the one up here, it says find the z-scores that correspond to the following ages. And so those ages are 26 and 32. All right, now it's helpful for us to remember that the mean was 30.7 and the standard deviation was 5.97. So that's, you need those. All right, so now we're going to find the z-score for each. So the z-score for 26, so just recall the z-scores are x minus mu over sigma. So the z-score of 26 is 26 minus the mean of 30.7 and divided by 5.97. So this would require a calculator most likely. If you wanted to use that, let me just pull up a calculator here. Let's pull up Desmos and just show you how you would use that. So what I would do is, let me just show you, if you do 26 minus 30.7, right, and then divided by 5.97, you can see hopefully that they have, it's only dividing the 30.7 by the 5.97. So that's not going to work. So you got two choices. One choice is to do this in two calculations. 26 minus 30.7, you get negative 4.7, and then do another calculation and do negative 4.7 divided by 5.97, and you get negative 0.787 if you were rounded to 3 decimal places. The other way to do it, I'm going to open up another rectangle here, number 3, to do this, is you can use parentheses and put parentheses around the 26 minus 30.7. And what that does is it says do that first. Do the 26 minus 30.7 first, and then divide it by 5.97, and you can see you get the same thing, negative 0.787. So again, this was on the top. We had negative 4.7 over 5.97, and we get negative 0.787. So that means, this means that 26 is negative 0.787 standard deviations away from the mean. So it's not quite 1 standard deviation below the mean. So this is definitely below the mean, which would make sense because 26 is lower than 30.7. So let's do 32. So the z-score for 32 would be the data value, which is 32, minus 30.7 divided by 5.97. So let's go to our calculator, and I'm going to delete those. So I'm going to go ahead and do the parentheses method. So 32 minus 30.7 is, if you look here, you can see what it is. It's 1.3. And then divided by 5.97, and we get 0.218. So I'm going to write that out on the other screen here. And this would be 1.3 on top divided by 5.97 in the denominator, and that's 0.218. That's positive, so it's above the mean. So that means that 32 is 0.218 standard deviations above the mean. All right. So, a couple more examples. So this one, SAT and ACT again. They have a mean. This time the mean of the SAT is 500 with a standard deviation of 100, and the ACT has a mean of 18 with a standard deviation of 6. It says that they're normally distributed, and I'm just going to tell you guys what that means is that both of the data sets make symmetrical histograms. Okay, so it says you score 550 on the SAT and a 24 on the ACT. On which test did you have a better score relative to everyone else who took the test? So what I want you to do is pause the video and find the z-score for 550 on an SAT and the z-score for a 24 on the ACT using this up here, and then decide who did better, the person who scored 550 or the person who scored 24. Again, you must find the z-scores first. So pause the video and then come back and we will go over the answer. All right, so hopefully you calculated these. And basically, it looks like the person who scored 24 on the ACT did better. The person who scored 550 on the SAT has a z-score of 0.5. So just if you were doing this real quick, you would have done 550 minus 500 over 100, and that ends up being 0.5. Had you done the ACT one, that is 24 minus 18 over 6, and you end up with 1. On the number line, here's the mean is 0, has a z-score 0. Here's 1. The SAT score is 0.5, so it's about right there. And the ACT score is here. So who did better? The ACT score was definitely higher relative to the other people who took that test. So the ACT score of 24 is better than an SAT score of 550. All right, so moving on, bell-shaped histogram. So this is the outline of the tops of a histogram that is symmetrical. We call it a bell-shaped histogram. We can also call it a normal distribution. I want to go ahead and introduce that vocabulary of normal, the word normal, right now in association to this bell-shaped curve. So anytime you see a bell-shaped curve, another word for it is a normal curve. You can also, instead of curve, you can call it bell-shaped histogram. You can also say normal distribution. They all mean the same thing. And for all of these, the mean, the median, and the mode are all in the middle. All right, think about this. The mode is the highest point, or the ones that occurs the most, so this would have the highest frequency. So that's mode. Median is in the center, and then in this case, the mean is the same thing. So that sets us up for empirical rule. The empirical rule is a set of characteristics that apply to this bell-shaped normal curve. The empirical rule, as I said, it's only going to apply to data sets whose histograms are symmetric and bell-shaped. Okay, and so it basically, this rule is a set of 3 characteristics. All right, so these characteristics are as follows. So the first one is that approximately 68% of the data will be within 1 standard deviation of the mean. So if you look here at this illustration below, here's the mean in the center. And if you go out 1 standard deviation below the mean and 1 standard deviation above the mean, that is about 68% of the data. So 68% of the data falls between 1 standard deviation below and 1 standard deviation above the mean. Okay, and so then the next characteristic is that approximately 95% of the data will be within 2 standard deviations of the mean. So from the mean, if I go up 1 standard deviation, 2 standard deviations, I'm right here. If I go down 1, 2 standard deviations, I'm right here. So if I add 2 standard deviations and get a value and subtract 2 standard deviations and get a value between those 2 values, that's approximately 95% of all the data. So if you go out 1 standard deviation each way from the mean, that's 68% of the data approximately. If you go out 2 standard deviations each way from the mean, that's approximately 95% of the data. And then 99.7% of the data will be within 3 standard deviations of the mean. So if I go from the mean, if I go up 1, 2, 3 standard deviations right here, and if I go down 1, 2, 3 standard deviations right here, that's approximately 99.7, which is almost all of the data. 99.7, there's only 0.3% left. So almost all of the data fall within 3 standard deviations of the mean. So those are the 3 characteristics, and this is a little illustration beneath it to kind of help you see that visually. So again, approximately 68% of the data is within 1 standard deviation of the mean. Approximately 95% of the data is within 2 standard deviations of the mean, and 99.7% of the data is within 3 standard deviations of the mean for data that is bell-shaped and symmetric. And this, again, is the empirical rule. So it says the calculator screen below represents the average and standard deviations for the U.S. Census Bureau project for the percentage of the population aged 65 and over for each state and District of Columbia. The distribution is symmetric. And then it says what are the boundaries for 95% of the data and what percent of the data falls within 11.566 and 14.932. So first let me talk about the calculator screen. Just to remind you, notations, X bar is mean. It represents, on this calculator screen, it represents both population mean or sample mean, whichever one you were trying to find. It doesn't differentiate. It uses the same symbol for both. So remember, mean is something that we do need for the formula. And the other thing that we need for the formula is, in this case, the population standard deviation. So that notation, remember, is sigma for population standard deviation. That's right here. So you want to pull those off the screen first. And this is what are the boundaries for 95% of the data. So what I find helpful, I'm going to go to this blank screen and I'm going to write down what our mean was. Our mean was 13.249. Right there. Mean is 13.249. And the standard deviation is 1.68. If I round to 3, it's 3. 1.683. And what I find helpful here is to actually draw this out. So we actually draw curves a lot in this class, so you want to go ahead and get used to that. So I draw out a nice curve. Okay, again, the calculator represents the average and standard deviation for the U.S. Census Bureau projection for percentage of the population age 65 and older, and it did say that the distribution was symmetric. So here we go. So we're going to put the mean in the middle. That always goes in the middle. So the mean was 13.249. And so what I suggest to students that they do is to build the empirical rule, like illustrate the entire thing, no matter what the questions ask. If you know that empirical rule is going to be applied here, just go ahead and do the whole thing. So what you're going to do is you are going to add the standard deviation 3 times. So you're going to add 1.683, and you're going to add it again, plus 1.683, and then you're going to add it again. And you can use your calculator to help you do this, but you're going to add it 3 times. All right, so the first time we add, I believe you get 14.932, and then if you add it again, you get 16.615, and if you add it again, you get 18.298. If you need to pause the video and to draw this out, or to add these numbers to make sure you get the same thing as I got, then go ahead and do that. All right, so we add the standard deviation 3 times from the center, which is the mean, and now we're going to subtract it 3 times from the center. So when I go the other direction, I'm going to subtract 1.683, and I'm going to get 11.566. And then I'm going to subtract it again. And I'm going to get 883. And then I'm going to subtract it one more time. And the reason we're subtracting 1.683 is because 1.683 is the standard deviation. And it looks like the last time we subtract, we get 8.2. All right, and so then what I do is, you can extend these lines if you want. But really what we want is underneath here. If I go out 1 below, so 1 this way and 1 above, 1 this way, I get these 2 numbers, 11.566 and 14.932. So if we go out 1 each way, that's approximately 68% of the data. So 68% of the data falls between 11.566 and 14.932. Then if I go out 2 standard deviations, so 2 below, so 2 negative 1.683s, and go above 2 1.683s, I get 9.883 below, and 16.615 above, and that we said was 95% approximately of the data. And then if we go 3 each way, 1, 2, 3, 1, 2, 3, we get these numbers. We get 0.82 and 18.298, and that we said was 99.7% of the data. And so once you have that, then you can answer any of the questions that they have up here. So let's scroll back up and see what those questions are. What are the boundaries for 95% of the data? So let's look. So 95% of the data falls between 9.883 and 16.615, because 95% is between 2 standard deviations above and 2 standard deviations below. So go up here and write that. So it falls between 9.883 and 16.615. All right, and again, the work is right here. And then it says, what percent of the data falls between 11.566 and 14.932? So 11.566 is right here, and 14.932 is right here, and you can see that that is 68% of the data. Approximately. All right, so I do find it easier to draw it out first and then use that to answer the questions. So you can see here, another way to do it is to do it with little formulas. All right, so just want to go back up real quick to the characteristics. So you could do this with a formula. You could do the mean plus or minus 1 standard deviation. So you could do mean minus 1 standard deviation and the mean plus 1 standard deviation. Those would give you the boundaries. For 95%, that would be the mean minus 2 standard deviations and the mean plus 2 standard deviations. And then for the third one, that'd be the mean minus 3 standard deviations, the mean plus 3 standard deviations. Now, that's what you're actually doing when you're creating the little visual here that we did there. But that is a quick way to do it. And that's what I've got here. For 95%, that was 2 standard deviations. So I did the mean minus 2 standard deviations. So if you look, the mean 13.249 minus 2 times the standard deviation 1.683, and we get 9.883. And then you do the reverse with addition instead, you get 16.615. So you can use this formula, but I do tell you it is much easier if you draw it out. So that's what I will be doing pretty much from here on out. This is just illustrating the same thing, talking about how you can create it like we did up here. So let's move on to another example. The weights of adorable fluffy kittens are normally distributed with a mean of 3.6 and a standard deviation of 0.4. What kitten weights are bound the 68% of the data? What kitten weights bound 95% of the data? And what kitten weights bound 99.7% of the data? So why don't you pause the video, draw out the normal curve, fill in, again, mean is in the middle, go 3 up, 3 down, fill in your percentages, and then answer these questions. And then when you unpause, we will go over the answers. Okay, so if you've unpaused it, hopefully that means you've worked it. We're going to put 3.6 in the center, and then we're going to add 3 standard deviations, and we're going to subtract 3 standard deviations. And so what we're adding is we're adding 0.4 every time. So if I add 3.6 plus 0.4, I get 4. And then if I add 0.4 again, I get 4.4. And if I add 0.4 again, I get 4.8. If I subtract 0.4 from 3.6, I get 3.2. If I subtract 0.4 again, I get 2.8. And if I subtract 0.4 again, I get 2.4. And then if we fill in these percentages, we know between 1 below and 1 above, that's 68% of the data. And then 2 below to 2 above is approximately 95% of the data. And 3 below to 3 above is approximately 99.7% of the data. So when it says what kitten weights bound 68% of the data, 68 is between 3.2 and 4. So we'll write that down, 3.2 and 4. And then 95% of the data is between 2.8 and 4.4. And then 99.7 is between 2.4 and 4.8. All right, so you can see how quick that goes. You know, you create this little diagram, and then you can answer basically any of the questions. All right, empirical rule retirements. It says the mean retirement age is 64. The standard deviation, with a standard deviation of 3.5. If the population is approximately symmetrical, answer the following questions. What percent of the data is between 57 and 71? What percent of people retire between ages 60.5 and 67.5? And the same thing between 53.5 and 74.5. So again, pause the video, create your diagram, and see if you can answer the questions. Unpause, and we will go over it. Okay, so here we go. We have the mean in the middle, which is 64, and the standard deviation is 3.5. So I'm going to add 3.5 3 times, and I'm going to subtract 3.5 3 times. And I'm going to fill in the numbers that I got. When I added 3.5 once, I got 67.5. If I added the second time, I got 71. If I added it the third time, I got 74.5. This is a 5 there. And then when I subtracted it, I got 60.5 and 57 and 53.5. So again, 1 standard deviation each way is 68%. 2 each way is 95%. 3 each way is 99.7%. So answering the questions, the first question is what percent of people retire between the ages of 57 and 71? Well, that is 95%. So I'll put that right here. And then it says what percent of people retire when they're older than, oops, sorry about that. I moved on to the wrong screen. Let me go back up here. This was 95%. And then what percent of people retire between 60.5 and 67.5? So that looks like it is 60.5 to 67.5 is 68%. And then what percent of people retire between the ages 53.5 and 74.5? That's the only ones that are left. And it looks like that is the 99.7%. Okay, I'm going to change it up a bit. We're going to use the same scenario, a mean retirement age of 64 with a standard deviation of 3.5, and it is symmetrical. We want to know what percent of people retire when they're older than 57. And so if you'll recall, we know that between 57 and 71 is 95%, but that's between those two numbers. We want to know 57 and older, 57 and above, and it doesn't stop at 71. So whatever we're looking for here is greater than 95%, so we need to figure out another way to go about this. And there's actually several different ways that you can figure this out. It's kind of like a puzzle. Just a couple things. We know the in-betweens. We know between here and here is 68, between here and here is 95, between here and here is approximately 99.7. But if we shaded the entire curve, this represents 100% of the data. 100% of the data is underneath the entire curve. Okay. The other thing is, if I were to split this in half right here at the 64, because it's symmetric, this would be 50%, and this is 50%. 50% of the data is on the left, 50% is on the right. I'm going to take this a little bit further before we start answering the questions. Let's say between here and here, we know that that is 68% of the data. But if I split this in half because it's symmetrical, I could split the 68 in half, and you have 34% on this side and 34% on this side. So we can use all of these facts to kind of try to figure out percentages that are not necessarily illustrated on the initial chart. We still have enough info that we can use to find them. So let's look at the first question. It says, what percent of people retire when they're older than 57? So again, there's a couple different ways that you can find this. So I'm going to show you a couple different ways. We're going to get the same answer every time. So it's just using characteristics about this graph. So let me locate 57. Here it is right there. And I do know something about it. I do know that it's attached to that 95%. It's on the other side of the boundary of 71. So between 57 and 71, I know that that's 95% of the data. So what I could do is, well, I need to know, basically this is what I need to know. I need to know from here, this line here, I need to know all of it. I need to know all of this, all the way to the other side, like past the 71, everything. I need to know all of it. All right, so one way to do this is to say, okay, let me split it in the middle, and at the 64, I know that the right side that's shaded, I know that that's 50% of the data. I do know that, right? Because the whole thing is 100. It's symmetrical. If I split it in half and I shade one full side, that's 50% of the data. Now, I can quickly figure out what is between here and here because it's attached to this 57 and this 95%. So I know from here to the 71 is 95%, but if I go from 57 just to the mean, that's half of the 57. I'm sorry, half of the 95. So if I were to divide 95 divided by 2, I would get 47.5%. 47.5%. So again, it's because if you go between here and, let me mark it here, that's 95%. If I go from the boundary 57 to the center, that's 47.5 on each side. So then what I could do is I could say 47.5% plus the 50%, and that gives me 97.5% is above 57. So 97.5% is above 57. All right? So I want to show you that that's not the only way that we could arrive at that answer, because like I said, there are several different ways that you can do this. Erase all of this. Okay, so again, 57. I can use the fact that I know between here and here is 95%. And so if I know between here and here is 95, all I need to find is this part and add it to the 97, right? And that would give me this part here plus that right edge, and that would give me the full percentage that I need, because again, I'm looking for above 57, and I know the center is 95. So this is what we can do. We can take the fact that we know the entire thing is 100%, right? And if I say 100% minus that 95% in the center, that it leaves 5%. So this is what I know. I know that between here, I know that these two together, these two outer sides, the outside of the 95%, that has to be 5% of the data, because the whole thing is 100, and if this is 95, then this left side and this right side together should be 5%. And because it's symmetrical, I can say that each one is half of 5%. So divide 5% by 2, and we get 2.5% over here and 2.5% over here. If you add them together, you do get 100%. So now I just want to add this 95% and this 2.5%, and that will give me the percentage that is above 57. So it's still 95 plus 2.5 is still 97.5%. So why don't you pause the video and try these next two. What percent of people retire when they're older than 60.5%, and what percent of people retire when they're younger than 53.7? And then when you're ready, we will go over both of those. Okay, hopefully you're ready. I had to reconstruct part of this because I was trying to delete things and I deleted part of it. All right, so now we're trying to figure out the percent of people who retire is older than 60.5. So here is the 60.5 right here. So a couple different ways to do it. I can take the fact that I know that this is 68% in the middle, and then all I need, so I need that, but then I need this area to the right as well. So 68 plus whatever that is. So to figure that out, I can do 100 minus 68. That gives me, 32%. So that means that this side over here and this side over here together is 32%. So if I split that in half, that leaves 16% on either side. So, 16% over here, 16% over here. So what percent is greater than 60.5? It'd be the 68 plus the 16. So what is that? 84%? Right? Another way you could do it is you could say, well, I know that this side, this is 68, and I know this is 16 and this is 16. So if I do 100 minus 16, so subtract this out, it would give this whole side, which is also 84. The other thing that you could do is you could split this down the middle and say this is 34 and this is 34, right? Actually, what you could do is we'll just say the left side is 34, and then this whole side here is 50. So 50 plus 34 is also 84. So lots of different ways to get those numbers. All right, so I think the easiest way to do this is just to erase the curve. I'm just going to leave those highlighted. Okay, so the last one is what percent retire when they're younger than 53.5? So here's 53.5. All right, so what we could do is we could say, well, I know that between 53.5 and 74.5, that is 99.7% of the data. And then I could subtract that from 100 and get 0.3. And then, so this side here and this side here together make up 0.3. So if I divide that by 2, 0.3 divided by 2 would be 0.15. So it's 0.15% over here and 0.15% over here. So what percent is younger than 53.5? It'd be 0.15%. So a very small percent that is. All right, so there we go with those. All right, so one more thing. Empirical rule applies to when the data is symmetrical, but what if the data is not symmetrical? We introduce Chebyshev's rule. So we use Chebyshev for any data set at all. It could be symmetrical. It doesn't have to be symmetrical. You can use Chebyshev for any of it. Although I will say if it is symmetrical, empirical rule is going to be a little bit better and a little bit more accurate. I mean, Chebyshev will be accurate, but empirical rule will be able to narrow things down a bit more. But Chebyshev will work for any data set at all. But typically we use Chebyshev when the data is not symmetrical. And so basically we have a couple different rules here. At least 75% of the data is within 2 standard deviations of the mean, and at least 89% of the data is within 3 standard deviations of the mean. And so again, if the data is bell-shaped and symmetrical, we use empirical rule. If it isn't bell-shaped, we use Chebyshev. I do want to add one in here. At least 95% of the data are within 4.5 standard deviations of the mean. So that's an extra one that I didn't have in there. So if you go out 1, we don't have any percentages for that. So you notice this one starts at 2 standard deviations. So if we go out 2, instead of being 95%, it's 75% at least, not approximately, at least. That means it could be 75% or more of the data is within 2. At least 89% of the data is within 3. So if we go out 3 standard deviations, it's 89 or more percent. And then if we go out 4.5 standard deviations, 1, 2, 3, 4, and then a half standard deviation, that's at least 95% of the data. Okay. It says the mean for systolic blood pressure was 120 with a standard deviation of 10. The data is not symmetrical. Use Chebyshev to describe the data. I just want to show you that you can draw this out just like we were doing before. All right, so what I usually do for Chebyshev is, let's see, the mean is 120 and standard deviation is 10. Okay, so what I usually do is instead of drawing a curve, I just draw a line because I don't know if it's going to be, I don't know what the curve is going to look like. So 120, and then I'm going to go out 1, and again, the standard deviation is 10. So I'm going to go out 1 and get 130, go out 2, so I added 10, add 10 again, I get 140, add 10 again, I get 150. Now, for this one, you can add, so we went out 3, but this one can go out to 4.5. So there's 1, 2, 3. 4 would be 160. 5 would be 170. halfway between 160 and 170 would be 165. So that's 4.5. 4.5 is 165. If I subtract 10, I get 110. Subtract it a second time, I get 100. Subtract it a third time, I get 90. Subtract it a fourth time, I get 80. And subtract it a fifth time, I get 70. So halfway between 4 standard deviations is of 80 and 5 of 70 is 75. All right, so if I'm filling this out, there are no rules, no characteristics for one standard deviation each way. So we just use the 110 and the 130 to help us to get to 2 standard deviations. So 2 standard deviations would be from 100, so that's 2 that way, 2 this way, to 140, and that's at least 75%. And then if we go out 3 each way, so that's 90 to 150, that's at least 95. I'm sorry, I said that wrong. 89%. And then if you go out 4.5, so that was out 3 each way, 1, 2, 3. If we go out 4.5, so that's from the center 1, 2, 3, 4.5, and you go 1, 2, 3, 4.5, right? We're going from 75 to 165. That's at least 95% of the data. And then when it says, this one just says the mean was 120, standard deviation was 10. It says use Chebyshev to describe the data. So you can just, this is the description right here. No, I've got it, kind of written out. At least 75% of the people had a systolic blood pressure between 100 and 140, which is what I have here. And they also said between 90 and 150 was at least 89%, but we're taking this a little bit further than what I had on that other screen, all the way out to 4.5 standard deviations, which is 95%. Okay, and then I did want to give you a little formula. You can figure out the percentage for any, if you know the number of standard deviations you want to go out, you can figure out the at least percentage with this little formula here. So I'm going to add this to the Chebyshev rules slide. So at least 1 minus 1 over k squared of the data fall within k standard deviations of the mean. So if I knew I wanted to go 5 standard deviations out, I would do 1 minus 1 over 5 squared, and that would give, so k would be 5. That's the number of standard deviations I would go out. And then that would give me the proportion of data that falls between those boundaries within those 5 standard deviations. So you can use this formula. This does show up in the homework, which is why I wanted to introduce it. All right, so real quick, the mean score on a statistics test is 80 with a standard deviation of 10. The data is not symmetrical between what 2 scores is at least 75% and between which 2 is at least 89. So you can pause the video, come back, check your answer. Okay, so here we go. If 80 is in the middle and we go up 10, that'd be 90. 10 more would be 100. 10 more would be 110. I can keep going to 4.5, but I don't think I have to do that here. Let's see, if we go down, that'd be 70, 60, 50. I'm going to go ahead and do the 4s. So if I go out 4, so I just want to mark the mean so I remember where that is. 1, 2, 3, 4 would be 120. 5 would be 130, so a half would be 125. And then if I go down 10 more here, that'd be 40, and then half would be 45. So if we were doing this, I would say between 60 and 100 would be your at least 75%, right? Because that went out too. 89 would be your 50 and your 110. So this is between here and here. That's your 89%. So 75 is between 60 and 100. 89 is between 50 and 110. If I ask what would 95% be, you would say 95 would be 1, 2, 3, 4 and a half would be 45 to 1, 2, 3, 4 and a half to 125. So if I had between 45 and 125, that would be at least 95% of the data for Chebyshev. Okay, so I think that is all. This has been a very long one, but I think that takes care of everything. If you have questions, please let me know.